Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section 3.1 on quadratic functions. We previously introduced the concept of graphing basic quadratic functions back in section 2.2, and we even talked about how to graph transformations of quadratic functions in section 2.3. Our goal here is to generalize the concepts a little bit so that we can graph any quadratic function, even if it has extra terms, if it's all been multiplied out, right? Something like ax squared plus bx plus c is not something we can handle through strictly the methods of transformations that we were looking at previously. So our goal in this section then is to be able to build up the information that we need in order to identify the key features of the graph just by looking at the equation and using that information to, of course, graph it once we're ready. So first things first, we already know that the shape of the graph of a quadratic function has the shape that we call a parabola. The parabola could either open upwards, like we see here, or, as we saw in the transformation section, if we had a negative a in that section, it reflected the graph vertically, and we ended up having a parabola that we would now say opens down, or opens downwards. We're going to be able to tell which way a parabola opens purely based off the equation, just like we could back in the transformation section. Now the most important point on the graph of a parabola, and it's going to be the center of our graph when all is said and done, is of course the vertex. So we will be looking at formulas to help us figure out what the vertex of a quadratic function is based off of the equation. And then if you were to draw a vertical line through the vertex, then any parabola will be symmetric about that line, meaning the right half and the left half of the graphs are mirror images or reflections across the axis of symmetry. And the axis of symmetry is just always a vertical line drawn directly through the vertex. We also have the concepts of x and y intercepts, which will be exactly the same as they were when we first started talking about them when we introduced lines. The x-intercept is where the parabola crosses the x-axis. The y-intercept is where the parabola crosses the y-axis. To solve for those, we're just going to plug in 0 for the other variable. Something worth noting in this section, however, is that not every quadratic function will have x-intercepts. For example, if we have a parabola whose vertex is up in quadrant 1, but it opens upwards, this would be a graph that never crosses the x-axis at all. It won't have an x-intercept. You can find that out, or maybe it would be better to say you can tell, because if you try to solve for the x-intercepts from the equation by plugging in 0 for y, you will get imaginary solutions. So if you end up with imaginary solutions, no x-intercepts. Now a parabola does travel forever to the left and forever to the right. Its domain is negative infinity to positive infinity. So because of that, the graph will always pass the y-axis once. So you will always have a y-intercept. And then last but not least, another important fact related to the vertex is that it's either what we call the minimum of the graph or the maximum of the graph. If it is a parabola that opens upwards like this, then the vertex is down at the bottom. It is the lowest point on the graph. So in this case, we would say it is the minimum. And the minimum value would be the y value of the vertex, because the y values are the actual function values. And similarly, if we have a parabola that instead opens downwards, then the vertex is going to have to be at the top. In this case, we would say that the y value of the vertex will end up being the maximum, the largest point on the graph. All right, so those are all the key features of the graph. This is a section that is very front-loaded on information. So we're going to talk about methods for figuring out all of these things And then we're just going to jump into a bunch of examples of figuring them all out for a bunch of different equations of quadratic functions. So first things first, you're going to commonly see quadratic functions written in two different forms in this section. The first form is the same form that we saw back in the transformations in section 2.3. So a times x minus h quantity squared plus k. This is sometimes called completing the square form because you get a form that looks like this by completing the square of the multiplied out version. This form tends to not be as easy to look at until you know what to look for. Once you understand the topics in this section, you're going to find that this transformation form is actually a lot easier to work with than one that's everything's been multiplied out in. The other form is, of course, once everything has been multiplied out and all like terms have been combined. So all you have is an ax squared plus bx plus c, where a is not equal to 0. You at least need an x squared term. This one's a little bit trickier to work with, but it's mainly just because of the vertex. The vertex is harder to find with this form, but everything else is really going to be the same. So let's start with one of the key features of the graph that you can tell just by looking at the equation without any manipulation whatsoever. And that's whether it is a parabola that opens upwards or a parabola that opens downwards. And a good place to start might be to think about it in terms of the transformations that we talked about back in section 2.3. So we know that the base graph, just y is equal to x squared, the one we performed the transformations on, is a parabola whose vertex was at the origin and it opens upwards. So you can kind of think as opening upwards as the base state of the parabola, the default. What we saw then is if a out front was negative, that caused the graph to be reflected vertically. And so then it would be a parabola that opens downwards. Negative x squared would be the graph of x squared, just reflected down. Now, if a is a large positive number, say 5, 10, 100, then the graph would be stretched vertically, but it would still open upwards. And so because of that, the way the graph opens is determined purely by the sign of a. If a is positive, then the graph stays in its default state of opening upwards, but if a is any negative number at all, then it causes the vertical reflection to happen. So if a is positive, it opens upwards. If a is negative, it opens downwards. Now, as for the other form, ax squared plus bx plus c, if you compare these two forms for the equation of a quadratic function, you might notice that they have some letters in common. One being the variable x, but that's our independent variable. That's what we're going to plug things into. So we're not so concerned with it. It's the constants that we're interested in here. The other letter that they have in common is a, and that is for a reason. If you were to complete the square of ax squared plus bx plus c, the b and the c get tangled up and become new things, h and k. Those are not equal to each other, right? H is its own thing, k is its own thing, different from b and c. That's why those letters don't carry over. But this a out front stays out front. It's the same a. And so this a, the coefficient of the x squared, the quadratic coefficient is sometimes called, tells us the same information as the a from transformations. So if a is positive, if the x squared term is positive, then the graph opens upwards, and if the x squared term is negative, the graph will open downwards. Right? So that is the same no matter which form of the equation you're looking at. The only difference is knowing where to look for a. For the transformations, it's the thing in front of the x minus h quantity squared, outside of the parentheses, whereas for the form that's been multiplied out, it is just the coefficient of the x squared. Next up, let's talk about how to find the most important point on the graph, and every problem in this section, in some form or another, is going to require you to end up finding the vertex. And the formula for the vertex varies depending on what form you're looking at. And this is really going to explain why the transformation form is so much easier to work with. So in the form a times x minus h quantity squared plus k, the vertex is just hk. Again, as always, the minus sign inside of the parentheses flips whatever you're seeing here. Right? This is just straight up a transformation. We know that y is equal to x squared has a vertex at the origin, 0, 0. So if you're given a transformation like this, it's just being shifted h left or right, opposite direction of the sign in the parentheses. So that means the x value of the vertex will end up at h, and it's getting shifted k up or down. So the y value of the vertex will end up at k. All right, so again, very nice form because you can just look at the equation and pick out the vertex. Clearly not quite so nice when working with the other form. So this is going to be a formula that you need to remember. And it is for the x value in particular of the vertex. For the form where it's been multiplied out, ax squared plus bx plus c, the x value of the vertex is at negative b, the coefficient of x, over 2 times a, the coefficient of x squared. And again, to kind of relate the two, if you were to complete the square of this ax squared plus bx plus c, that negative b over 2a is what ends up in the place of h. And so that's how that formula was actually derived in the first place. Which is also why they named it a new letter, so it didn't look quite so messy in the final form. Now, if you have trouble remembering this formula at the beginning, you might find that if you have already remembered the quadratic formula, which you should have, negative b plus or minus the square root of b squared minus 4ac all over 2a, the x value of the vertex is basically the quadratic formula if you drop the plus or minus square root. And so that could be a useful way to remember it when you're first getting started. All right, very important formula. I can't stress this enough. Make sure you know that the x value of the vertex is negative b over 2a. Large chunks of this section rely on that. There's also a formula for the y value of the vertex. It's even a little bit messier than this one, but frankly nobody knows what it is. Or nobody bothers to memorize what it is maybe more appropriate to say. Because just like when we were graphing back in section 2.2, if you know the x value of an ordered pair and you want to find the y value of an ordered pair, you just plug the x value into the equation. Same thing here. Once you find the x value of the vertex, you evaluate the function at that x value. Next up, we've got the axis of symmetry, that vertical line that goes directly through the vertex, and it follows immediately from the vertex. So let's do a quick review of what the equation of a vertical line looks like. If you wanted to draw a vertical line that goes through an x value of 2, what every ordered pair on that line has in common is that it has an x value of 2, 2 to the right. And so the equation just ends up being x is equal to 2. Well, if you have already found the vertex of the parabola and you need a vertical line to go through the vertex whose x value you will know at this point, then it's just going to be x is equal to the x value of the vertex. And in this case, I've already written it out in the form of the formulas. So either x is equal to h if you're in the transformation form, or x is equal to negative b over 2a if you're in the multiplied out form. But truth be told, in an actual problem, you'll have numbers for the vertex at this point. So it will be the same regardless. It's just x is equal to the x value of the vertex. Now this is important to note. A common mistake students tend to make when it comes to the axis of symmetry is that when I ask for it, let's say they found the vertex of the parabola and found it at 2, 3. I'll ask for the axis of symmetry, and I'll just be told 2. That is incorrect. That would be a wrong answer. The axis of symmetry is a line, and so its answer is the equation of a line, the equation of a vertical line. So this is not just nitpick about notation. This is the difference between a correct answer and an incorrect answer. If you're asked for the axis of symmetry, it is not just a number, it is an equation. X is equal to the x value of the vertex. That's very important. You would lose points for that. Just a few more points to finish things off. The x value of the vertex gives us the location for the axis of symmetry. The y value of the vertex is also important. As I mentioned previously, the vertex is either the highest point or the lowest point on the graph, the maximum or the minimum, and the y value is that maximum or minimum. So you have to combine this together with the knowledge of the way that it opens, which you determine from the sign of A. So if you figure out that the parabola opens upwards, think about what that would look like. Then the y value of the vertex would be the minimum. If your parabola opens downwards, then the y value of the vertex would be the maximum. And the last thing we'll be asked to solve for in this section before we graph are the intercepts. And again, just like when we were doing lines, if you want to find the intercepts, you plug in 0 for the other variable and solve. So to find y-intercepts, plug in 0 for x, and to find x-intercepts, plug in 0 for y. And that is all of the information for section 3.1. What we're going to do from here on out is just work our way through 4 different examples, 2 of each form, and we'll work our way down the checklist of the type of information we're expected to be able to determine and ultimately sketch the graph of each parabola. So we're going to start off with, again, the form that is a little bit easier to work with, the transformation form. And in example 1, we are given the quadratic function y is equal to x plus 3 quantity squared minus 1. In part A, they are asking us, how does the parabola open? So remember that a here is the coefficient in front of the parentheses. If you don't see anything there, it's implied to be 1. Right? There's not a negative sign out front. That's the key idea here. And so because there's not a negative coefficient for this parentheses, this is a parabola that opens upwards. In part B, we're asked to find the vertex, and that is just HK. Right? As always, the thing tangled up with the x is the x value. But again, opposite sign of what you see in parentheses. This is an x squared that's getting shifted 3 to the left. So the x value of the vertex will be negative 3, whereas k on the outside is much more straightforward. It's exactly what you see. Shifted 1 down, so the y value of the vertex would be negative 1. For the equation of the axis of symmetry, I need a vertical line that goes through an x value of negative 3, so that would just be the equation of the line, x is equal to negative 3. For part D, we're asked to find the maximum or minimum value on the graph and determine which, classify, is it a max or a min? That is the y value of the vertex. In this case, since we decided in part A that this is a parabola that opens upwards, the vertex will be at the bottom, so we would say that this has a minimum of negative 1. And now something that we didn't talk about before, but we're going to cover right now, is the range of the function. And truth be told, you could determine that from the graph once you have finished graphing. That would be okay, but you can actually also just determine it from the vertex itself. So we just discussed the fact that this is a parabola that opens upwards and that its minimum y value is negative 1. So negative 1 and up are the y values of this function. So the range and interval notation then would be from -1, included, because the vertex is part of the graph, up to a y of positive infinity. In part F, we're asked to find the intercepts of the graph, and this usually takes a little bit more work, which is why I've given us more space to work with here. So why don't we start with what is usually the easier, the y-intercept. And if this form, the transformation form, has any downside, as opposed to working with the other form, it is the y-intercept. The y-intercept is super easy if you have ax squared plus bx plus c, because if you plug in 0 for x, the constant term is the y-intercept, whereas it does require a little bit more work in this form. All right, so since I'm finding the y-intercept, I'm going to plug in 0 for x. So this would leave us with 0 plus 3 quantity squared minus 1. Right, order of operations, parentheses first, 0 plus 3 would be 3. Exponent second, 3 squared would be 9. 9 minus 1 would give us 8. So that's the y value of the intercept. So as an ordered pair, x of 0, y of 8. Now the x-intercept for this form is usually a little bit easier on the other hand, because this is something that you can solve due to the nature of the form with the square root property. You won't have to manually factor when working with this form. So let's take a look now at the x-intercept. If it exists, because remember, they won't always. So for the x-intercepts, I'm going to plug in 0 for y. So we have 0 is equal to x plus 3 quantity squared minus 1. My goal is to get x by itself. So I can't take the square root like this, because remember, square root of a plus or minus b does not simplify. So I got to get rid of that minus 1 first. So I'm going to add 1 to both sides to move it across. Now I'll apply the square root property. So I'm going to go ahead and rearrange the term order as well, because I like my x's on the left, just personal preference. If I take the square root of both sides, we get x plus 3, just cancels out the square root, or the square rather, is equal to plus or minus, don't forget that, the square root of 1, but the square root of 1 is 1. And now I'm just going to subtract the 3 to the other side and put it in front of the plus or minus to make sure there's no confusion. Now, if there were square roots in this answer, I would leave it as is because it wouldn't simplify, but because it's not, you're expected to break up the plus or minus sign. So let's think about this. We've got two answers. We've got -3 minus 1, which would give us -4. Or we have -3 plus 1, which would give us -2. As ordered pairs, these would have y values of 0. So we would have the ordered pairs -2, 0, and -4, 0. And last but not least, we are asked to sketch the graph of the parabola. And this is one you could actually just do using transformations if you wanted to. So if you just want to use the methods that we covered in section 2.3, that would work just fine. In general, if you want to graph a parabola by plotting points, which is what we're going to need to do for the other form, ax squared plus bx plus c, you have to start with the vertex. And the vertex, remember, is the center of the graph. So the vertex we discussed previously was -3, -1, hk. So -3 will be my middle x value. So now I just need to pick one point to the left of the vertex, one point to the right of the vertex, and then I can connect the dots with the parabola shape. If I want to refine the shape with the graph, make it a little bit more accurate, you could go 2 to the left, 2 to the right. Pick 2 points in both directions. All right, so if I want something to the left of -3 on the number line, -4 would probably be a good choice. And if I want to pick something to the right of -3 on the number line, -2 would probably be a good choice, a number on either side. If you want to find the y values, you can just plug those back in. I'm going to cheat a little bit here though, because we actually discovered that those two values happen to be our x-intercepts on the previous slide. Those both have a y value of 0. If you did plug those in, you would get 1 squared minus 1, which would of course subtract to give you 0. So let's sketch the graph. So we've got our vertex at -3, -1. And if you go the same distance in both directions from the vertex, in this case I went 1 to the left to -4 and 1 to the right to -2, you should find that these y values are always equal to each other because of the symmetry of the parabola. It's symmetric around the vertex. And in this case, we get our x-intercepts of -4, 0 and -2, 0. Again, if you wanted to be really thorough, you could plot the y-intercept, which was up at 8, so it's somewhere way up here. All right, and so now I'm just going to connect the dots. Make sure you have no sharp corners on the graph. And also never let it go perfectly straight up. Something I see with the graphs of these sometimes, I'll have students who write just a straight U like this. That's not really representative of a parabola. They are always going left and right, so don't make them too steep. All right, and so this is the graph we're looking for. So let's take a look at one more example involving the transformation form. In example 2, we've got y is equal to -2 times x plus 3 quantity squared plus 4. So try pausing the video here and see if you can find the solutions to parts A through E of example 2. So I'm going to go through this fairly quickly. For how the parabola opens, that's determined by the number in front of the parentheses, which is negative this time. And so because it's negative, it flips and opens downwards. The vertex, HK, opposite sign for H, would be -3, +4. The axis of symmetry would just be x is equal to the x value of the vertex. The y value is the max or min, and since this parabola opens downwards, the vertex is at the top, so this would be a biggest or maximum value, which we often abbreviate as just max, of 4. And as for the range, the biggest y value this time around is 4. And it goes forever down to -infinity. So the range would be from -infinity up to +4. Now try pausing and see if you can find the intercepts of the graph. All right, so for the y-intercept, we're going to plug in 0 for x. Common mistake, I'll see students just drop that whole parentheses. They assume it goes to 0, but that's not the case because of the addition on the inside. So inside the parentheses, we have 0 plus 3, which would be 3. That exponent is only going to apply to it. The -2 comes last, right? In the order of operations, exponents first, multiplication after. So this would be -2 times 9 plus 4, or -18 plus 4, which would give us a y value of -14. So 0 for x, -14 for y. For the x-intercepts, we're going to plug in 0 for y on the other side of the equation. All right, so again, my goal is to get the parentheses squared by itself. So I'm going to start by subtracting the 4 across to the other side. Then dividing that coefficient of -2 across. So we have x plus 3 quantity squared is equal to +2, a negative divided by a negative, square root of both sides, plus or minus square root of 2, which is not something we can simplify, it just is what it is. And then I'm just going to subtract the 3 across to the other side. In this case, because the square root stuck around, we can't really simplify that. It just is what it is. So if we needed to write this as an ordered pair, it's not going to be the nicest thing in the world. We've got a -3 minus the square root of 2, 0. And we've got a -3 plus the square root of 2, 0. And last but not least, try pausing and see if you can sketch the graph of the function. Right, so once again, 3 points will do, although you can graph more than 3 if you would like to get a better shape. So we've got -3, -4, or excuse me, -3, +4 for the vertex. One x value smaller, one x value bigger, one on each side. This time around, I am going to have to plug them back into the equation. There's no getting around it. So let's start with the -4. If we plug in -4, the inside of the parentheses, -4 plus 3, would be -1. But since that's getting squared anyway, this becomes a -2 times a +1, which would just give us -2, still with the +4 on the end. And -2 plus 4 would give us a +2. If you were to evaluate -2 in the problem, I'm going to save a little bit of space here. Inside of the parentheses turns out to be +1 this time around, which if you square it is still 1, times -2 would be a -2, plus a 4 would give you a +2, which again is what we would expect to see because of the symmetry of the parabola. All right, so now I'm going to sketch the graph. So we've got -3, 4. And then when we went 1 to the left, it went 2 down. And 1 to the right, it went 2 down. And so we're going to end up with a shape that looks a little bit like this. So now let's take a look at an example with the form that's a little bit trickier to work with. And again, it's mainly just part B that's different, the vertex. Everything else is going to be more or less the same. So starting with part A, we're asked how does the parabola open? So this time around, the A, the thing that determines how it opens, is the coefficient of the x squared. In this case, the x squared term is just 1 times x squared, positive. So this would be a parabola that's going to open upwards. The vertex takes more work. We can no longer just look at it and tell. So that's why you have to know the formula for the x value of the vertex, -b over 2a. So let's figure out what that would be. If b is +2, then this would be -2 over 2a, the coefficient of x squared, which again is just implied to be 1 in this case. So this is a -2 divided by a +2, which would give us a -1. So the x value of the vertex is -1. To find the y value, we're just going to plug it back in. So this would be -1 squared plus 2 times -1 minus 3. So this would be 1 minus 2 minus 3, or 1 minus 5, which would give us a -4. All right, from here on out, it goes a little bit more quickly. It's just like it was in examples 1 and 2. Equation of axis of symmetry is just x is equal to the x value of the vertex, -1 in this case. This is a parabola that opens upwards, so the vertex will be a min. The y value tells you what that min is, so this is a minimum of -4. And then for the range, this parabola is -4 and up. So it would be from -4 to positive infinity. Now we're asked to find the intercepts of the graph, starting with the one that is by far the easiest in this form, the y-intercept. So if we plug in 0 for x, again, every term but the constant always goes away. And so this would just be -3 for the y-intercept. And the x-intercepts are sometimes at least a little bit trickier this time around. If you're lucky and you have a quadratic formula that factors nicely, then it's not a big deal. But potentially you could have to solve this using either the quadratic formula or completing the square. Because if we plug in 0 for y, you end up with a quadratic equation to solve. Well, fortunately for us, this one does factor nicely. So this would be an x plus 3 times an x minus 1. Just to double check, x squared, 3x minus x would be a 2x, minus 3 checks out. I'm going to set each of those equal to 0 and solve, which would give me a -3 and a +1. So +1, 0, -3, 0. Last but not least, we want to sketch the graph of the function. All right, so starting with the vertex, -1, -4. Let's get my center point. I want one smaller than -1 to the left, so -2 would be a good choice. And one bigger, so 0 would be a good choice. Not the only things you have to use. So now to figure out the y values, I'm going to plug them back in. So if I plug in -2, careful with parentheses, that has an effect here, especially with the square term. That's going to become +4, -4, -3. So the 4's cancel and we just get the -3. And if we plug in 0, we actually end up with a y-intercept of -3. All right, so our vertex is at -1, -4. Then we've got -2, -3, 0, -3. But in this case, I'm going to go ahead and plot the x-intercepts as well because they worked out nicely, just to get a little bit more shape. And that's just one more in both directions, so to +1 and to -3. And so our parabola would look something like this. So let's take a look at one final example. So once again, try pausing the video and see if you can find the answers to parts A through E of example 4. So starting with the way the parabola opens, the coefficient of the x squared is negative this time, so this is a vertical reflection. This one opens down. Vertex requires a little bit more work. All right, so negative b, the coefficient of the x would be a negative 4 this time. So that's going to swap to becoming a positive 4, divided by 2a, the coefficient of x squared, which is a negative 2. And so a positive 4 divided by a negative 2 would give us a negative 2. So that's the x value of the vertex. I'm going to plug it in to find the y. Again, careful with parentheses. So I'm going to replace the x's with parentheses. And then inside those parentheses, I'm going to plug in negative 2. So this negative would get squared away to be positive 4, but this minus sign out front would turn it back into a minus 4. And then we have a minus 4 times a minus 2, so a plus 8. And a minus 4 plus 8 would give us a positive 4. Axis of symmetry would be x is equal to negative 2. Because this one opens downwards, this graph would have a max of positive 4, the y value of the vertex. And if 4 is the biggest y value, the range would be from negative infinity up to 4. For the intercepts, for our y-intercept, we're going to plug in 0 for x, which again makes the x squared and the x term go away. And since there is no constant this time around, we just get 0. X of 0, y of 0. So in other words, the origin is our y-intercept this time around. For the x-intercepts, I'm going to plug in 0 for y. And because there is no constant term, we can use the greatest common factor method. I'm going to factor a negative x out of both terms, which would leave me with a positive x to the first power and a plus 4. And if I set each of those equal to 0 and solve, we get x is equal to 0 and x is equal to negative 4. 0 as an answer makes sense because if the origin is a y-intercept, it also has to be an x-intercept. But we have an additional one as well at negative 4, 0. And last but not least, we need to sketch the graph. So with our vertex of negative 2, 4, one to the left, one to the right. Plug them in. Careful with parentheses. So if we plug in negative 3, this would be a minus 9 plus 12. So that would give us a positive 3. And because of symmetry, I think we're going to find that the same is true for the other as well. If not, that's a sign that we've done something wrong, be it the vertex or the evaluation. This is going to become a minus 1 because of the minus sign out front, plus 4, which also is a positive 3. Right, so we've got our vertex of negative 2, 4. To the left and right, we fall 1. And again, I'm going to plot the x-intercepts because those worked out nicely here. We had the origin, 0, 0, and we also had one at negative 4. So that's something I would only plot if they happen to end up being nice like they were in this case. And so we get a graph that looks like this. And that is it for section 3.1. It's a very tightly focused section overall. It's just about determining information about a quadratic function from its equation. So make sure you can follow through on all of the parts that we talked about in this section, no matter which form of the equation you're given. Completing the square form, the transformation form in other words, or the multiplied out form. Now, one thing to note before we wrap up here is that we didn't specifically see an example of a parabola in this section that didn't have x-intercepts, but we did mention earlier on in the section that that can occur. That happens if you get imaginary roots when you're trying to solve for the x-intercepts. So do keep that in mind. Imaginary answers are the same as saying no intercepts, but you can actually determine that before you even start trying to solve the equation if you're careful to look out for where the vertex is and how the parabola opens. So for example, if you have a parabola with a positive y value, meaning it's above the x-axis, and it also opens upwards, then you don't even have to check for x-intercepts. You'll know that there aren't going to be any. The graph doesn't cross the x-axis. Similarly, if you had a parabola whose vertex had a negative y value, it was below the x-axis, and it opened downwards, that would be another example of a case where you just can't possibly have x-intercepts. So you can sometimes save yourself a little bit of work if you think in advance, is there going to be x-intercepts? Is it worth solving the equation? With that said, as always, if you guys have any questions about the material, please make sure you let me know, and I will see you in the next video.